Hello everyone, this is section 8.1, Solving Systems of Linear Equations by Graphing. In this unit, we will be dealing with a topic known as systems of linear equations. When we talk about systems of equations, we are talking about two or more equations that are solved together. We will only be looking at linear equations for now, but just remember that we have already talked about other equations such as exponential equations. In future math courses, you'll be dealing with other types of functions, such as trigonometric and logarithmic functions. And you may also be dealing with linear systems in 3 dimensions at some point. At the top of your screen, you're going to see two equations appear. X minus 2y equals 10, and 2x plus 3y equals 6. When solved together, this would become a system of equations. So our goal is very simple. Find the point at which the two lines cross each other. But the real way to say this, or the more mathematical way to say this, is find the point at which the graphs of the equations intersect each other. And here's an example. So let's graph both equations and see what we get. You're going to see off to the right of your screen that both these equations have already been graphed for you. The first equation is 2x plus 3y equals 6. And you're going to see that in purple. The second equation is x minus 2y equals 10, and you will see this equation in green. After we graph both lines, we can see that they do intersect each other. It appears to be that the point of intersection is 6, -2. Well, let's check to make sure the point 6, -2 satisfies both linear equations. You will notice that I have plugged in 6, -2 into equation 1. And when I did so, it did work out correctly. I then plugged in 6, -2 into equation 2. And again, I was able to get a true statement. Therefore, 6, -2 is the solution to both equations. So we will take our system of linear equations and do 4 things. 1. Graph the first line using the skills we learned earlier this year. 2. Graph the second line using the skills we learned earlier this year. 3. Determine the point of intersection. And 4. Check to make sure the point satisfies both equations. There are a few special notes about graphing linear systems. Case 1 is parallel lines. As we know, parallel lines never intersect each other. So if we have a system of linear equations where two lines are parallel, we will not have a point of intersection. And in formal math terms, we would say there is no solution. Case 2, same line. Sometimes the two linear equations in a systems problem will be the exact same line. When we graph these lines, we will only see one line. In this case, the two lines intersect each other everywhere. So it would be easier to say that the lines are the same line. Pay attention for each of these cases. If you have parallel lines, then there is no solution. And if you have a line that is the same line, well, then the answer would be everything. So here is some super intense terminology. Formal mathematicians use the following terms to communicate the 3 types of solutions that we can get from a system of linear equations. You can get 1 point, like our first example. This is called an independent system of linear equations. Well, you can also get parallel lines, in which case we call this an inconsistent system of linear equations, where there's no solution. And lastly, you can have the same line, which is called a dependent system of linear equations, where there's infinitely many solutions. And just to recap, the purpose of systems of linear equations is to find the point of intersection of the graphs of both lines. And we call this the point, our solution. And so here's a little graphing linear systems in technology. So here's my first equation, y equals 2x minus 3. And here's my second equation, y plus 2 equals negative 2, and in parentheses, x minus 3. And there's a graph. So the first equation is in slope-intercept form. So think back to what you know about slope-intercept form. This must mean that I have a slope and a y-intercept. The slope of this function is 2. This would tell me to move up 2 units and to the right 2 units. I also have a y-intercept, and that y-intercept is at 0, negative 3 on the y-axis. So if I go to graph this, I'm going to start at the y-intercept of negative 3, and then I'm going to go up 2 and to the right 1, continuously until I have a line. And you will see that line appear on the graph to your right. The second line is in point-slope form. Again, you should recognize this form. I'm going to pull out the point and the slope of this equation. The slope happens to be at negative 2. Now this would mean that I would move down 2 units and to the right 2 units. The point is 3, negative 2. Remember that when you pull the point at a point-slope form, you want to think the opposite. So although I see x minus 3, I'm really pulling out a positive 3. And vice versa with the y plus 2. I see a positive 2, but I'm going to pull out a negative 2. So I'm going to graph the point 3, negative 2, and then I'm going to apply the slope to that point. And you will see that line appear. Now if I try to figure out where these two graphs intersect, they don't intersect as nicely as they did before on our previous example. So therefore, sometimes it's actually easier to maybe not solve by graphing or possibly use a graphing calculator to help you, because I'd have to really eyeball where that intersection point is. It doesn't intersect very nicely. So on page 6 in your notes, you're going to see the review of steps on the TI-83-84 Plus graphing calculators. I understand that while you're at home, you probably don't have a graphing calculator, but that's okay. We'll review this in class. But here are the steps, so just make note that this is the page to look over if and when you have to use a graphing calculator. You will see that I provided the graph that I got on my calculator, and the intersection ended up being at 1.75, 0.5. So no wonder why I had trouble kind of eyeballing where that intersection point is. It was much easier to try and do that on a graphing calculator. I have a couple words of advice for you, and here's number 1. Form of linear equations. So just because a given problem has a specific form of a linear equation, like standard slope-intercept or point-slope form, it doesn't mean you have to leave it that way. You can always change the form if it makes the problem easier for you. We learned this skill earlier this year. If you need to, you can review your previous work on this topic. Words of advice number 2. Those pesky fractions. We just can't seem to get away from them. You don't have to suffer with fractions. If you don't like them, find the least common multiple to multiply each term by. Find a number each denominator goes into nice and even. So the example I have below, I have 2/3 x minus 1/4 y equals 5/6. I would want to find a least common multiple. So if I look at the denominators 3, 4, and 6, I can change all of those into 12s. And so I'd want to multiply the numerators and denominators accordingly to have the denominator all be 12. And words of advice number 3. Modeling problems. We will be returning to modeling problems with linear equations. We have done this in the past. If you have forgotten your skills or if you're a little rusty, you may want to look back on your previous work on this topic. In the modeling problems for this section, we will write 2 linear equations, graph these equations, and find the solution. This will end our notes on section 8.1, so please make sure that you have everything written down and prepare yourself for class by looking over what the questions will be for this section.